Resolving power of a diffraction grating. Already in our last class, we have completed about what is diffraction grating and what is the spectrum in the formation of diffraction grating. But today, we want to learn about resolving power of a diffraction grating, because finally we got the expression for resolving power of the diffraction grating lambda by d lambda is equal to small and capital N. So for this here, first of all, what is the resolving power of a diffraction grating? Already we know that about what is the resolving power. The resolving power of a grating is, which is defined as the ability to separate the spectral lines which are very close to each other. Already in our previous slides, we have defined the resolving power of a given instrument, optical instrument. Here we are taken as a grating, here the grating element here. Say the width of the slit is here a plus b. This is the width of the slit a plus b. This is a, this is b. So total is a plus b. Say this is slit, width of the slit is a. This is b. So total is a plus b is the width of the slit. So let us consider parallel beams of light of wavelengths lambda and lambda plus d lambda. So here we have considered two wavelengths of wavelength lambda and lambda plus d lambda. So their wavelength difference is very small, that is d lambda, which are already incident on the slits. Then we incident normally on the diffraction grating. What happens? If nth principal maximum of lambda and lambda plus d lambda are formed in the direction of theta n and theta n plus d theta n respectively. Of course, here this is the wavelength lambda. Say from this point A, which is incident, light is incident normally on this diffraction, slit of this grating element, diffraction grating element of wavelength lambda. So this lambda, which is making an angle of diffraction theta n, so that this lambda, which has the principal maximum, this one. So this is the principal maximum of the first wavelength lambda, which is diffracting with the angle of diffraction theta n. So it's this is the principal maximum of lambda, and this is the first minimum of lambda. Say this is the first minimum of lambda wavelength. This is the principal maximum of lambda. Okay, and consider another wavelength. So by changing a small wavelength, that is lambda plus d lambda, this is another wavelength which is also diffracted with the angle of diffraction theta n plus d theta n. So its principal maxima is this one. This is the at a point Q. Just you have to observe the principal maxima. So the principal maxima of lambda plus d lambda is at a point Q, and its first minima is formed at a point P. So according to the definition of resolving power of a given instrument, we have to recollect the previous definition, that is Rayleigh's criteria. If whenever two spectral lines are said to be resolved, if this is the here the central maximum of the first wavelength lambda coincides with the first minimum of the another wavelength lambda plus d lambda. Already in our last class we have defined the Rayleigh's criteria. So that is, according to Rayleigh's criteria, whenever two spectral lines are said to be resolved, what is the condition? That is the central maximum of the one wavelength lambda is coincides with this central maxima is coincides with the first minima of lambda plus d lambda. Okay, so we are taking these two equations here. So here for the principal maximum by wavelength lambda, the grating equations. So grating's equation written as, so this is width of the slit. Actually we know that what is the condition for maxima, what is the condition for maximum and minima? Actually we know that in the diffraction grating, what is the condition for minima? A plus b sin theta is equal to n lambda. Okay, so actually at the center here, at the central maxima, already we have defined here, previous slides we have defined d sin theta is equal to n lambda actually. Yeah, here d sin theta is equal to m lambda. D sin theta is equal to m lambda. Of course, here it is n lambda. So a plus b sin theta is equal to n lambda. So that is equation number 1. For wavelength d lambda, So it's a central maximum here. A plus b sin theta n plus d theta n is equal to n into here lambda తీసుకున్నాము ఇక్కడ lambda plus d lambda తీసుకుంటున్నాము. So this is okay for the wavelength lambda. This is for wavelength lambda plus d lambda. So we know that these are the only the principal maximum by wavelength lambda, okay, on the screen actually. But we know that for the minima, so minima kuda manaki lambda తీసుకోవచ్చు. So lambda యొక్క minima q అనే పాయింట్ దగ్గర ఫామ్ అయింది. Lambda plus d lambda యొక్క minima, first minima p అనే పాయింట్ దగ్గర ఫామ్ అయింది. So we know that for that minima a plus b sin theta n plus d theta n is equal to n small n into capital N plus or minus 1 by okay into lambda by capital N. So this is already derived equation actually. So by using these equations 2 and 3 here, so by using equations 2 and 3, so both are same here. So a plus b sin theta n plus d theta n is equal to, because this is the central maximum of lambda plus d lambda n actually. So this is the first minimum of here, okay, first minimum of the lambda plus d theta n actually in the direction of lambda plus d lambda actually. So in the direction of, this is the first minima, this is the first minima. The central maximum of lambda plus d lambda is equation 2, but equation 3 which represents the first minimum of lambda in the direction of lambda plus d lambda n, okay, that is in the direction of theta n plus d theta n. So that's why we are taking this equation. So these two equations are using, okay, by equating these two we got here m into small n into lambda plus d lambda is equal to small into capital N plus or minus 1 divided by capital N into lambda is equal to, by simplifying this equation we got here finally small n into here small n into capital N is equal to lambda by d lambda. So very simple. So that is equation number 4. So that's why we are defining the resolving power of a grating element. The resolving power of a grating is equal to the ratio between wavelength and the difference of the wavelengths, that is lambda and lambda plus d lambda. So lambda by d lambda is equal to small n into capital N, where small n is the order of the spectrum, where capital N is number of spectral lines on the grating element actually. So it is a very simple equation.
Sir, for equation 3.
Cheppandi.
Equation 3.
Equation 3. This is the minima equation in the direction of lambda plus d lambda. Hello. This is the minima equation in the direction of lambda plus d lambda. Inka more equations nahi avi ivaledu. So we just to remember this equation, because this equation represents the equation of minima in the direction of lambda plus d lambda. That's why according to Rayleigh's criteria, so both are equal. So by simplifying this one, so we got an expression for the resolving power of the grating, lambda by d lambda is equal to small to capital N. Okay. Next, coming to double slit interference, actually interference from a double slit experiment, diffraction grating and single slit. So these are the comparisons between actually among these three actually here. Actually double slit తీసుకుంటున్నాము. So wavelength actually d sin theta is equal to m lambda, and this is here diffraction grating experiment. This is for this is diffraction grating. This is intensity of the light from single slit in diffraction phenomenon actually. Okay, this is only for your convenience, just only for your previous knowledge. Okay, just we have to revise your previous topics. Okay, so these three diagrams represents that is the comparison among these three here. Coming to here, what are the other applications of diffraction? Only here we have learned about the diffraction of only light is observed. Diffraction of light rays from single slits or double slits here. Okay, so మనకి డబుల్ స్లిట్స్ మనకి సిలబస్ లో లేదు, బట్ అది కూడా ఉంటుంది. డబుల్ స్లిట్స్ నుంచి లైట్ రిఫ్రాక్ట్ అవుతున్నప్పుడు ఇంటెన్సిటీ ఎట్లా ఉంటుంది అనేది కూడా కాన్సెప్ట్ ఉంది. బట్ మనకి సింగిల్ స్లిట్ డైఫ్రాక్షన్ ఇచ్చే సిలబస్ లో కాబట్టి అదే చెప్పుకుంటున్నాం. బట్ వాట్ ఆర్ ది డైఫ్రాక్షన్ ఆఫ్ అదర్ వేవ్స్? దట్ మీన్స్ ఓన్లీ లైట్ వేవ్స్ డైఫ్రాక్ట్ అవుతున్నాయా? లైట్ వేవ్స్ లో సపోజ్ ఎక్స్రేస్ ఉన్నాయి. Because in the actually in 2012, the year 2012 was the 100th anniversary of the X-ray diffraction actually. So because X-rays are the part of the electromagnetic spectrum, as we know that X-rays, gamma rays, cosmic rays. So all these are the different ratios in the electromagnetic spectrum. Already we know that about what are the different ratios in the electromagnetic spectrum. So if we recall the previous knowledge regarding electromagnetic spectrum, so we are starting from radio waves to cosmic rays. Actually, if we consider about their wavelengths and frequencies, their wavelength is in decreasing order from radio waves to cosmic rays, but whereas the frequency is increasing order from radio waves to cosmic rays. Okay, already we know that about this previous knowledge. So radio waves, microwaves, infrared waves, visible light, UV light, ultraviolet rays, X-rays, gamma rays, cosmic rays, etc. So because of their high frequencies, they're highly energetic. That is UV rays, X-rays, gamma rays, cosmic rays. Okay, so here the X-ray diffraction technique is very important. X-rays are also diffracted. From which type of slits? Okay, X-rays diffract outunnayi, light waves diffract outunnayi. So what we know that what is the condition for the diffraction phenomenon of light waves? What is the condition? So if the wavelength of the instant light lambda is comparable to the size of the slit A, if lambda is comparable to is approximately equal to A, then only the light is diffracted from the slit, actually from the edges of the slit. But here, in case of X-ray diffraction, these X-rays are incident on the slit. But what is the slit here? Generally, what is the slit here? We are taking that is crystals. Crystals are taken as the crystals, because these X-rays incident on the crystal surface. Because in the crystals, they're having different crystal structures actually. Suppose in any type of crystal, actually, generally here, this is the X-rays, this is crystal. Coming to this picture here, say a scientist Lave in 1912, actually, he got Nobel Prize for his crystal diffraction, that is X diffraction, in 1914. So he got Nobel Prize. So here the X-rays tube, by using X-ray tube, just we are sending, we are passing so X-rays onto the crystal surface. These X-rays are incident on this crystal surface. So why we are using crystals? Because here, yeah, coming to this picture here, this crystal is consisting of planes, atomic planes. This is the atomic plane, upper plane. This is the lower plane. Say that means in the crystalline solids, actually the atoms are very closely bound to each other, and they are aligned in they're having a geometrical shape, a particular geometrical shape and size. That means all the atomic planes which are arranged in a particular direction. So the distance between any two atomic planes is very small, that is d, which is in the order of 1 angstrom unit actually. So the distance between any two atomic planes is taken as 1 angstrom unit, which is in the order of 1 angstrom unit. So the distance between these two atomic planes will be taken as a slit. Whenever light is incident on this slit, which is diffracted. So from this slit. So that's why the distance between, in the crystals particularly, the distance between any two atomic planes will be taken as a slit. So that these X-rays, their wavelength is in the order of the slit. That is where the slit is here, the distance between two atomic planes. Any two atomic planes with distance and the that will be taken as a width of the slit. That will be matching to the wavelength of the X-rays. That's why the X-rays are incident on only crystalline solids only. Particular, okay, that is here. Coming to this one. So lattice spacing typically here. This is the here A is equal to. So this is 100. This is 200. Okay, this is lower plane. So this is A. So 1 angstrom is equal to 10 power minus 10 meters. But here, the wavelength here, the wavelength of the slit here, the slit width is here, that is 1 angstrom particularly. So in the actually diffraction of X-rays, we got a very important equation, that is Bragg's law. 2D sin theta is equal to n lambda. Already we have learned in a previous class. 2D sin theta is equal to m lambda. Of course, its derivation is also there in this picture here. So coming to the 2D X-ray diffraction supplemented by electron and neutron diffraction. So not only X-ray diffraction, but also neutron diffraction and electron diffraction is also there. So coming to what is the energy difference, what is the wavelength here, what is the energy of each diffraction phenomena. For the X-ray diffraction phenomena, E is equal to h nu, hc by lambda. So lambda is equal to hc by E. So that is lambda is equal to 1 angstrom తీసుకున్నప్పుడు energy ఎంత వస్తుందంటే, so 12 kilo electron volts వస్తుంది. So that is energy of the X-ray. Okay, so next is electrons తీసుకున్నప్పుడు actually is equal to 150 electron volts. So in case of neutrons తీసుకున్నప్పుడు is equal to 0.08 electron volts. Already X-ray diffraction అని తెలుసు, because this X-ray diffraction is a very important phenomena in the actually in research, particularly in the study of the crystalline structures. Suppose whenever you have to produce, you have to prepare any crystal, any new material, immediately you are going to study that it's a structural structure of the given compound. So you have to prepare one compound, one crystal, or one new material, that is nanomaterial. So immediately you are going to X-ray diffraction. X-ray is characterization తీసుకెళ్తాం, because first of all you must learn about which type of structure is there, is exhibiting that new type of material. So that is X-ray diffraction. And electron diffraction is already you know about electron diffraction, and neutron diffraction it is okay. ఇది మీకు కొత్తగా వచ్చింది. సో ఈ ఎలక్ట్రాన్ డైఫ్రాక్షన్, న్యూట్రాన్ డైఫ్రాక్షన్, ఆల్రెడీ ఎలక్ట్రాన్ డైఫ్రాక్షన్ గురించి మీరు విన్నారు. సో లవర్ క్లాసెస్ లో మీరు విన్నారు యాక్చువల్లీ ఎలక్ట్రాన్ డైఫ్రాక్షన్, that is Davison-Germer experiment లో ఎలక్ట్రాన్ Davison-Germer experiment లో ఎలక్ట్రాన్ డైఫ్రాక్షన్ గురించి విన్నారు మీరు యాక్చువల్లీ. So because here electrons, because in Davison-Germer experiment actually the electron wave is, the electron beam is already instant on the nickel crystal, actually it will be diffracted. Actually this is the experimental proof of the wave nature of electron. So electron wave nature ni etla prove chestam adigaru actually, because de Broglie matter waves concept expand chesinappudu. So de Broglie actually introduced the concept of matter waves actually, because light has dual nature. Similarly matter has dual nature అని చెప్పేసి అంటాడు. లైట్ కి డ్యూయల్ నేచర్ ఉన్నప్పుడు matter కి డ్యూయల్ నేచర్ ఎందుకు ఉండకూడదు, యాక్చువల్లీ ఉంటుందని చెప్పేసి his hypothesis అనేది he has given as a thesis and he has submitted that thesis in the university, so that he got PhD award for his so 10 pages of thesis regarding de Broglie matter waves. But it has no experimental proof for his actually he has no experimental proof actually. He has no experimental proof. So once tarot call cheyanu. So he has no experimental proof. Theoretically he explained, de Broglie explained, he calculated the wavelength of the matter wave lambda is equal to h by mv or h by p. But then after the wave nature of the electron is experimentally verified by Davison-Germer actually. So Davison-Germer అనే వాళ్ళు ఎలక్ట్రాన్ కి వేవ్ నేచర్ ఉందని చెప్పేసి ఎక్స్పెరిమెంటల్ గా ప్రూవ్ చేస్తారు. సో de Broglie అయితే యాక్చువల్లీ వాడు థియరిటికల్ అని చెప్పాడు. థియరిటికల్ గా ఫార్ములా ఇచ్చేసి లాంబ్డా ఇస్ ఈక్వల్ h బై p ఇస్ ఈక్వల్ h బై mv అని చెప్పేసి ఈక్వేషన్ ఇచ్చేసి వాడు de Broglie వేవ్ లెంత్ యొక్క వేవ్ లెంత్ క్యాలిక్యులేట్ చేసేస్తాడు, మ్యాటర్ వేవ్ వేవ్ లెంత్ క్యాలిక్యులేట్ చేసేస్తాడు. Because any particle of mass m which is moving some velocity, definitely that particle is associated with the wave, that wave is called de Broglie matter wave. So the wavelength of the de Broglie matter wave is given by lambda is equal to h by mv is equal to h by p అని చెప్పేసి అంటాడు. So but he has no experimental proof. So for their experimental that is de Broglie matter waves అంటే మ్యాటర్ కి వేవ్ నేచర్ ఉందని చెప్పేసి ఎక్స్ప్లెయిన్ చేయాలంటే మ్యాటర్ లో పార్టికల్స్ ఉంటాయి, అంటే ఆటమ్స్ ఉంటాయి, ఆటమ్స్ లో పార్టికల్స్ ఉంటాయి, ఆ పార్టికల్స్ ఎలక్ట్రాన్ ఉంటుంది. సో ఎలక్ట్రాన్ కి వేవ్ నేచర్ ఉందని చెప్పినట్లయితే సో ఆటమ్ కు వేవ్ నేచర్ ఉన్నట్లు, లేదా మ్యాటర్ కి వేవ్ నేచర్ ఉన్నట్లు అని చెప్పేసి డిసైడ్ చేసుకుని డేవిసన్ అండ్ జర్మర్ అండ్ జిపి థామ్సన్ అనేటువంటి సైంటిస్టులు, సో వాళ్ళు జిపి థామ్సన్ అండ్ డేవిసన్-జెర్మర్ వీళ్ళు ఎలక్ట్రాన్ డైఫ్రాక్షన్ అంటే ఎక్స్పెరిమెంట్ వాళ్ళు చేస్తారు. సో దాంట్లో ఎలక్ట్రాన్ హ్యాస్ వేవ్ నేచర్ అని చెప్పేసి ఫైనల్ గా ప్రూవ్ చేస్తారు. ఆల్రెడీ యూ హ్యావ్ దట్ కాన్సెప్ట్ ఇన్ ఇంటర్మీడియట్ కోర్స్ యాక్చువల్లీ de Broglie matter waves లో ఉంటుంది. సో ఎలక్ట్రాన్ హ్యాస్ వేవ్ నేచర్ అని చెప్పేసి ఎక్స్పెరిమెంట్ ప్రూవ్ చేస్తారు. ఆ ఎక్స్పెరిమెంట్ కి వచ్చిన వాల్యూ వేవ్ లెంత్ ఆఫ్ ది ఎలక్ట్రాన్ de Broglie వేవ్ లెంత్ ఆఫ్ ది మ్యాటర్ వేవ్ ఆ రెండు క్యాలిక్యులేట్ చేసుకుంటే ఎగ్జాక్ట్ గా అగ్రిమెంట్ వస్తుంది, ఎగ్జాక్ట్ గా ఈక్వల్ అవుతాయి. సో కాబట్టి వాళ్ళు ఏం చేస్తారంటే ఎస్ దిస్ ఎక్సలెంట్ అగ్రిమెంట్ బిట్వీన్ థియరిటికల్ వాల్యూ అండ్ ఎక్స్పెరిమెంటల్ వాల్యూ విచ్ ప్రూవ్స్ ఎలక్ట్రాన్ హ్యాస్ వేవ్ నేచర్ అని చెప్పేసి వాళ్ళు ఎక్స్ప్లెయిన్ చేస్తారు. అంటే ఎలక్ట్రాన్ డైఫ్రాక్షన్ అనేది మనం డేవిసన్-జెర్మర్ ఎక్స్పెరిమెంట్ లో చూస్తాం యాక్చువల్లీ. సో ఎక్స్-రే డైఫ్రాక్షన్ అనేది డెఫినెట్ గా మనకి ఎక్కడ యూస్ అవుతుంది, గ్యారంటీగా క్రిస్టల్ స్ట్రక్చర్స్ ఆ సిమిక్ యాక్చువల్లీ మనకి ఒక రీసెర్చ్ ఓరియంటేషన్ లో any material that is not only in the science but also in any field actually. ఒక క్రిస్టల్ కానీ ఒక న్యూ మెటీరియల్ కానీ ఏదైనా ఒక మనకి కొత్తది వచ్చిందంటే కొత్తది ప్రొడ్యూస్ చేస్తామంటే ప్రిపేర్ చేస్తామంటే దానికి క్రిస్టల్ స్ట్రక్చర్ మనం ఫైండ్ అవుట్ చేయడానికి ఎక్స్రే డైఫ్రాక్షన్ ఫండమెంటల్ గా యూజ్ చేస్తాం. సో దిస్ ఇస్ అబౌట్ diffraction. So these are bending of light at corners of the door. It is a very common example for the diffraction of light in our daily experience. That is, this is actually a diffraction grating. And last one is here. The light is here. The bending of light is from the here. So these are the plants, trees actually. So trees that is slits nunchi actually light bend avutundi. So this is also another example. So this is the best example of diffraction phenomenon. Okay, so this is about only the diffraction of light from single slit actually. So in this chapter we have very important question, that is the diffraction of light from single slit. And we have to calculate intensity. Okay, in single slit diffraction, that is quantitatively, and qualitatively. So that means this phasor diagram is very important. And also resolving power of diffraction grating is very important. Okay, so any doubts regarding this topic? Hello.
Sir.
Cheppandi, any doubts?